Welcome to this explainer. Today we're diving into what's essentially the ultimate cosmic detective story. We're taking a close look at NASA's Nancy Grace Roman Space Telescope. Slated to launch no later than May 2027, this incredibly powerful observatory is gearing up to completely revolutionize our understanding of the cosmos, and we're going to break down exactly how it plans to do that.
Ultimately, it boils down to these two monumental mysteries. What is the universe actually made of, and are we alone in it? Obviously, these aren't small questions. To tackle them, Roman is going to operate as an unparalleled investigator stationed out at the second Lagrange point, or L2, which is roughly 1.5 million kilometers from Earth. And from that super stable vantage point, it's going to hunt for new worlds and uncover the universe's darkest secrets.
Section 1. Meet the Cosmic Detective.
To really understand how Roman will crack these cases, we first need to look at its unique vision. Now, Roman is often called Hubble's wide-eyed cousin, and it's easy to see why. It actually shares the exact same 2.4-meter primary mirror size as Hubble, meaning it captures images with that same stunning resolution and sensitivity in the near-infrared. But here's the kicker. Roman is equipped with a 300-megapixel wide-field instrument, which gives it a totally staggering advantage.
A single snapshot from Roman's wide-field instrument covers a field of view at least 100 times larger than Hubble's infrared camera. Just think about that for a second. One single Roman image holds the equivalent detail of 100 pictures from Hubble. This means Roman can survey the sky up to 1,000 times faster, capturing vast, sweeping swaths of the cosmos in a fraction of the time.
Case 1. Unveiling dark matter and energy. Roman's first major case tackles the invisible macroscopic structures of our universe, starting with dark matter. Now, we obviously can't see dark matter directly, but Roman is going to hunt for it using a phenomenon called weak gravitational lensing. As light from distant galaxies travels toward us, it passes by these invisible clumps of dark matter. The immense gravity of that dark matter actually bends the light, slightly warping the apparent shape of those background galaxies. By measuring those minute distortions across millions of galaxies in its massive panoramic view, Roman will literally map out the hidden distribution of dark matter.
And then, of course, there's dark energy. This is that mysterious force causing the universe's expansion to accelerate. To investigate this, Roman's high-latitude time domain survey will track ancient exploding stars known as Type Ai supernova. Since we know exactly how bright these specific supernovae should be, we can use them as cosmic yardsticks to measure immense distances across space and time. By mapping these explosions alongside the distribution of galaxies, Roman is going to test exactly how this dark energy is pushing the universe apart.
Case 2. The Galactic Bulge Survey. From the grand scale of the expanding universe, Roman is then going to zoom right into our own galactic backyard to search for hidden exoplanets. For the Galactic Bulge Time Domain Survey, Roman will stare towards the center of the Milky Way, monitoring the brightness of hundreds of millions of stars. And it's going to do this incredibly fast, snapping images every 15 minutes over 72-day seasons. Basically, it's monitoring roughly 240 million star years just to catch some incredibly rare, fleeting events.
So why the rapid-fire imaging? It's all because of a technique called microlensing. When two stars perfectly align along Roman's line of sight, the closer star's gravity acts like a natural magnifying glass, bending and magnifying the light of the star way in the background. But if that closer star happens to have an exoplanet orbiting it, that planet's own gravity will create an extra, temporary spike in the star's brightness. It is an absolutely ingenious way to spot hidden worlds that don't even emit their own light.
And the scale of this survey is just mind-blowing. This massive statistical census is expected to discover over 2,000 microlensing exoplanets and over 100,000 transit planets. Roman will find everything from Earth-mass rocky planets to free-floating rogue planets drifting entirely alone in deep space. This is going to completely transform our understanding of how common planetary systems like our own actually are.
Case 3. Coronagraph, blocking the starlight.
But hey, finding planets through their gravitational pull is really only half the story. Roman is also bringing a revolutionary new forensic tool to image these exoplanets directly. Now, this is notoriously difficult because a host star can be 1 billion times brighter than the planet orbiting it. To pull this off, the coronagraph instrument uses a highly complex system of masks and large-format deformable mirrors, relying on a principle called destructive interference. It basically creates an opposite wave where the peaks of the stellar light match the valleys of the instrument's wave. When they interact, they perfectly cancel each other out, totally blocking that blinding stellar glare.
Once that starlight is canceled out, it creates what scientists refer to as a dark hole. Inside this deep contrast zone, post-processing can reveal the incredibly faint light of circumstellar dust disks and exoplanets that were previously just lost in the glare. This coronagraph is essentially a 3-month technology demonstration, but it could yield our very first visible light images of mature Jupiter-sized planets in reflected light.
So why does this specific tech demo matter so much to us? Well, proving that active wavefront control and ultra-low noise detectors can perform at this level in space is a vital stepping stone. It directly paves the way for future missions, like the proposed Habitable Worlds Observatory. That mission will use advanced versions of this exact technology to eventually find and directly image an Earth 2.0 in a star's habitable zone.
Section 4. An era of big data.
Fulfilling all these scientific missions means managing an absolutely unprecedented amount of information. Over the course of its primary 5-year mission, Roman is going to amass up to 20 petabytes of data. Because of its huge field of view and rapid imaging speed, the observatory will be downlinking roughly 11 terabytes of compressed data back to Earth every single day. And honestly, here's the best part. All of this is non-proprietary, open-access astronomical data, available immediately without any exclusive access periods.
To put 20 petabytes into perspective for you, that is the data equivalent of 10 million HD movies. Yeah, you're definitely not downloading that to your personal laptop. To handle this everyday cosmic scale, astronomers are shifting their paradigm. Scientists will use cloud-based analysis tools, like the Roman Research Nexus, bringing the computing power directly to the data in the cloud. This means anyone in the astronomical community can jump right in and help sift through the clues.
With this massive volume of high-resolution, wide-field data, the discoveries absolutely will not stop at just dark energy and exoplanets. As NASA notes, this data will offer practically limitless opportunities to explore cosmic phenomena across all of astrophysics, from studying the evolution of ancient galaxies all the way to tracking small rocky bodies right here in our own solar system.
And that leaves us with a truly exciting prospect. As we inch closer to that May 2027 launch date, the anticipation is definitely building. Roman will map the invisible, it'll census hidden worlds, and it's going to pioneer the technology we need to eventually find an Earth twin. So, when Roman finally settles into its orbit 1.5 million kilometers away and opens its wide eyes, what completely unexpected dark secrets will it find waiting for us in our cosmic backyard?